Hello, welcome to CSC 351, Introduction to Data Science. Today's topic is on linear regression. So far we studied the basics of linear algebra, probability, and then these are two pillars of data science, and also we showed how using pandas library we can read data and do the pre-processing, namely cleaning data, removing outliers, and also dealing with the missing values, and also normalization, and also some preliminary visualization to see how the data look like. After we prepared our data, now we are ready to do some statistical pattern recognition, some prediction, and then further analyze the data in order to gain more insight or prediction about our data. So here the machine learning algorithms come to play. So machine learning algorithms can be branch out to four groups, but two major methods in machine learning is supervised learning and unsupervised learning. So for today's lecture we are focusing on supervised learning, and first of all I'll give you a formal definition about supervised learning. There are two types of supervised learning in machine learning: classification and regression. So we will focus on linear regression, about the basics and how we can train a model, how we can find the parameters, and then how we can validate a regression model. And also I give you some basic of codes how we can validate our model, and then in the next video we'll talk about classification and also the matrix we are using for classification. So if you want to have a big picture view of machine learning, this is a very nice diagram. So basically we are given some data and we assume that these data are pre-processed and ready for analysis. Then we start by a tree-like structure in order to do what kind of method or algorithm we should apply to our data. So we start by just having our data. Usually we need to have enough samples in order to be able to have a statistical inference or prediction about our data. So if you don't have enough data, usually we don't have a good understanding of the underlying distribution of our data. So usually it is recommended, if you don't have enough data, you should try to have and collect more data sets. We consider anything less than 50 samples from a population doesn't reflect the true behavior of that population. Nonetheless, there are some special applications in which it's extremely difficult to get more samples. Still we can apply some statistical analysis on our data, but in order to have a more accurate and confident inference on our data, we should have, as a rule of thumb, more than 50 samples. So if you have more than 50 samples, then we are looking in our data. These data are some sort of categorical data or not categorical data. That means they're continuous or not continuous. based on if the data are from some categories or continuous, we can take different approaches. But they're mainly machine learning algorithms can be subgroups to classification, regression, and then dimensionality reduction and clustering. So regression and classification are a member of supervised learning. So we call it supervised learning because we have some input and output about our data. So I will elaborate on that shortly. If you don't have the output, and then we usually use unsupervised learning, and most of the unsupervised learnings are based on clustering. There could be a hard clustering or soft clustering. We will consider later on one clustering technique based on k-means in this course. And also sometimes you wanted to do the dimensionality reduction and then do another analysis where we already talk about dimensionality reduction. So these are four categories of algorithm. When we wanted to analyze our data, we usually use them. Either we do regression, classification, clustering, or we try to do dimensionality reduction or compression. So this is a very nice diagram. I would suggest to print it and put it on your desk anytime you're having a problem. That gives you a very good a big picture view of machine learning algorithms. Okay, so as I said, supervised learning techniques in machine learning can be categorized into two groups: classification and regression. So here I will give you a formal definition for classification, and then also I will give you an example of a classification technique, and then we will talk about the regression in details, and then how we perform regression, mainly linear regression, and how we find the parameters of our model and how we validate our model. So these are in a pipeline of a machine learning algorithm is you should know the input features, and you should know the output, and you should know what kind of model you should apply to your data, and then after that, how to validate your model. These are four steps in any machine learning algorithms. So classification. So I wanted to, as I said, classification and regression are both belongs to supervised learning, but I wanted to just here emphasize what's the difference between classification and regression. So for classification, we usually, all these problems look like having a function. You have an input, you have an output, and you have an unknown function. So, so you're all familiar with a property of function. So we can consider a function as a black box where you have an input and you have an output. But what's important in here to pay attention, what is the input to this function and what is the output to this function. So as you note in here, the input to this function is a vector, and the output to this function is a categorical variable. So we know that a categorical variable is a variable can take a limited of fixed possible numbers, or it could be also not numbers, some classes, some strings. So anyway, it just comes from a set of limited options or objects, but we can always translate this object, this string, to numbers. So the output from a classification is a scalar, which we denoted by y. So we know that this is and a scalar. Which y belongs to a set of different labels. Y, let's say k, where k is different labels for the input. So, and also we note that x is a vector. X is a vector. So this is a function will take a vector and will generate a scalar. And that scalar gives us the label of this input vector. The vector elements are called features of this classification. So these features could be anything. Could be numbers, could be some names, could be date. There are an object. So for different problems, we may want to convert them to some continuous number or some other type of numbers. But here we don't talk about details. We only consider we have collected P features as an input to a classification, and based on these features which we collected from a phenomena, we wanted to find the label that this object belongs to. So that is a classification. So, and then what's the goal in classification? The goal in classification so we call this y as output and x as input, like a function. So, and then for each object, in general, we have some labels. We have collected the features and we have the label. So this is why we call this technique supervised learning. That means we already know for each object its label. We have collected samples from some populations, and then from this population we know the features and also we know the output. But for limited number of samples from this population. So, so if you have some, let's say, n number of pairs, also note that again in here y in here is a scalar and x is a vector, and the superset I denotes the ith sample. So for instance, y2 x2, it means the second sample from this population. It's extremely important to understand the difference between sample and features. I notice many students mix them up. So you should know when you're talking about a classification problem, two questions. The first two questions you need to ask: how many samples do I have? And what is the dimension of the feature space? So in here, the dimension of a feature space is P. And how many samples do I have is N. So don't confuse these two numbers. So, what type of problem we wanted to solve? The problem is as follows. It's basically an optimization problem. I'll give you some samples from this population where for each object I have collected some features and I have the labels, and then I have the pair of feature label, and I wanted to find the function that maps this input feature to the output label. So we can say, okay, if this is the domain of X, if this is the domain of X, and then this is the domain of Y, where domain of X are vectors, there's a function which this is a function which map the input to the output. The goal is to find this function. The goal is to find this function based on some given inputs. So these input data are usually called training data. So based on this training data, we wanted to find the function. So it's obvious that we cannot exactly find the actual function, but we wanted to find a function which satisfies some requirements. So what are those requirements? The requirements are as follows. So if you have some other objects in the population, well, let's say we randomly select some objects from this population for which we have the feature and we have the label, and we hide them, and then we estimate a function f, let's call it f hat. So this hat in here means this is an estimation. Usually we put a dot in arguments in order to show this is a function with some input arguments. So if you want to be more specific, instead of this dot, I should have an x with an arrow on the top. Then for new pairs, we wanted to see if we just feed the feature, we can get the true label for that feature. So if you wanted to see if you have a good estimate of this function, then this estimation should be able to also predict for the unseen value during the training. So this is important point about the training and testing classifier. So we wanted to test the classifier such that it can also predict the data that are not used for the training or for the optimization problem. Because if you use the same data for testing the function, the estimation function, as the data you use for training, then that's a problem occurs that's called overfitting. That means your model can predict the data for which you did the training, but if you present the new data, new features, then because the classifier has not seen this data, then it will do a wrong prediction or wrong label. In this case, your classifier is not generalized, and that's a huge problem. And sometimes we think we have designed a good classifier, but when there's some unseen data coming and see very poor performance. I will show you what is the overfitting and how we can treat the overfitting in classification. So as I said, the process of estimating f is called the training phase, and the process of finding the prediction based on the feature space for a label is called prediction, inference, or test. So a classification task has two stages. The first stage is called the training, where you are given some pairs of input and output. Then based on this pair of input and output, you identify a function, and then after you train this model, you find the parameters of this model, then you test your model based on some unseen data. So what is this function? The answer to this question is there are a number of different functions designed for different purposes, and therefore we have many types of classifiers. We have classifiers starting from a very simple form like a naive Bayes, we have support vector machine, we have logistic regression, we have random forest, we have decision tree based classifiers, we have neural network classifiers, we have Boltzmann machine classifiers, and this list can continue and go on and on. But what is important in here, you understand what is the basic of the classification, what you wanted to do. Otherwise, all of these classifiers are already designed, and the scientific Python libraries, they have them. You don't need to design a classifier, but what is important is you know what is the input and output, how to present an input, and how to validate your model, and understanding the difference between training and test data. So this is called a classification problem. So now, what is the regression? So regression is more focus of regression is on linear regression, but I will give you a general formula. So the regression is exactly very similar to classification, but with one major difference. And that difference is the output of the function where we fit the input features is a continuous variable rather than a categorical variable. So this is the main difference between a regression model and between a classifier. Classifier output is coming from a set of categorical data from some limited labels, but the output of a regression model could be any real number, a continuous values. So, but the rest is the same. We have a function, call this function f. The input still is a vector. We have feature space. We have p features, but y in here belong to real numbers. Y belongs to real numbers, and this is a continuous variable. And p is number of features. Again, we have some set of features and also the output. Now we wanted to basically having n pair samples from input and output, we wanted to estimate a function f hat as close as possible to a true function which based on which the output is generated, and then this function we call it as close as possible to true function when can perform well on the samples which are not used during training, namely the tested data. So we see that there's a very close link between regression and classification or classifiers. But the only difference is the output of a regression model is a continuous value. And for many problems, the output is not labeled, is not a category, but is a continuous value. So for those problems, in order to tackle them, we need to use a regression model. The other thing is, as I said, we mostly focus on linear regression. We mostly focus on linear regression. For linear regression, this function is linear. So this function is not a nonlinear function. So we call it a linear regression when this function is a linear function. I will explain what do we mean by a linear function, but the focus on when we talk about regression, for 80% of time we mean a linear regression, and linear regression means the function we assume that relate the input to output is a linear function. So I'll shortly talk about what is a linear function. So in order to wrap up this distinguish between difference between classification and regression, here I give you an example from a classification problem, and then in upcoming videos we talk more about classifiers, and then the focus of this course is mostly on neural networks because they are perhaps the dominant types of the classifiers for today's big data science problems. So it's good to focus on this type of classifiers and how to train them and how to evaluate their performance. So, but anyway, that function f could be anything, and you can also come up with your own classifier based on the function you're treating for your purpose. But this function should have some properties. We will talk about that shortly. So here is a very popular classification problem. You are given some set of images. As you see in here, I have different images of cars, animals, and then for each image, we also give you a label. We give you a label. So if this picture is an airplane, for instance, if I call this one, if I call this as the input feature in here, x as a vector, let's say this is sample, let's call this for sample 1, 2, 3, 4. So this is sample 4, This is the feature, which is the image, which is basically some pixels. And then what you wanted to do, for this feature, we have a label. What is the label for this one? Is airplane. So basically this is Y4. So I can say I have one pair in here, which is X4 and Y4. So as I said, the output, the label is now a string, is a word, but we can easily map the words to numbers, right? I can say, okay, I have 100 labels by a string, then I can map them to 100 numbers. It doesn't matter if there is a function, we can easily map a set of words to numbers. So that's not a big deal in here. And so for this example, for instance, if I wanted to see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means the label space has 10 different possible values, 10 different possible values. And then so I can write the Y belongs to one of these labels, Y1, Y2, all the way to Y10, because we have 10 labels. And then for this example, how many? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 100 samples. So if I wanted to see what is the number of samples, in here I have xi features and then yi. Sorry, y is not a vector, so y I, and then I is equal to 1 to 2 to 100. I have 100 samples from this population, 100 samples from this population. And then what is the dimension of feature space? Another important thing. So for images, usually we consider the number of pixels as a number of feature space. So if you have a two-dimensional image, which is look like a matrix, we usually flatten that matrix. And then if, for instance, consider each image is a, let's say 5 by 5 pixel, then the feature, the X dimension is belonging to R25, because we flatten that image and that would be a vector of 25. So a vector X, or feature space, or P, is 25. So here we go. Now we have 100 samples from this population. What is the task? The task is we wanted to find a function that can predict the name or contact of an image based on the image. So we basically want to present an image to our function, and function tells us what is this feature. This is what kind of animal, this is a bird, this is a cat, this is an airplane, and so on and so forth. This is a classification problem. So therefore we wanted to find a function. So what is this function? This function says, okay, if this is the function, then if x, which is a vector, is equal to a frog, this is a picture of a frog, then output should predict this is frog, the label. So this label should be a number. As I said, we can map the words from dictionary to numbers, and this is not a big deal in here. So this is basically a classification problem. This is a classification problem. This is a classification problem. How about now we can, so you got the basic idea of classification and the difference with regression. Now we go in more details into the linear regression. As I said, we focus only on linear regression. We have some nonlinear regression. The famous nonlinear regression is logistic regression, which is basically a classification. So we will talk about that when we talk about classifier. For now, we talk about the linear regression. So in linear regression, we assume the function that maps the input to output is a linear function. So that means the way that we wanted to find the output is a linear combination of the input features. So as you see in here, the output for sample I is equal to a linear combination of the input features. So I have p plus 1 features. So the first feature is called intercept. Intercept, usually we put this one intercept if the data have a bias. So in all of the regression model, we have this intercept unless you you normalize your data and take the vector y is zero mean or centered. But for the sake of the completeness, we assume that we have intercept in here. So now we have a feature vector. We have a feature space, and a vector A in here is called the coefficient vector. So the coefficient. So what is the task? The task is to compute these coefficients, linear regression coefficients. These coefficients also include the intercept value. Sometimes in some contexts they separate them to they call this coefficient as a slope and this one as an intercept, but in here we call them the linear regression coefficients. And also note that if you're in some context, they start by simple linear regression when you only have one feature. So basically your regression model is up to here. But we barely use this type of model. We usually collect a number of features from an object and then we wanted to compute the output. So, so one simple example is if you wanted to find a diabetes index, which is a continuous value for a patient, we may collect different features from a patient. Let's say we can measure his or her weight, his height, type of, the history of his disease, age, is a smoker, non-smoker, and some other features. This list can continue. And then we wanted to see if based on these features, which are xi in here, x1, x2, xp, can we predict the output? So in other words, when we talk about regression, we can also consider regression from another angle. And that one is if the output, which also called the response, or called also the dependent variable in the regression setup, can be explained by the input features. So these input features also called predictors or covariate or regressors. So we have some regressors or we have some features, and we wanted to see if these features can explain the output. In other words, if wanted to investigate that if these features are somehow related to the output, if they have any relationship, if they are dependent, if the output is dependent on these input features. So one way of doing this basically is based on what we studied so far, is based on correlation. We can find a correlation between output and each feature to see which are correlated. But the difference between correlation and regression, correlation only consider one feature at a time, but regression basically shows the contribution of each feature in order to generate the output. So this is important because for many real problems, you have collected lots of features and you have no idea. Studying each input output, it would be very time consuming. Usually we do a regression which shows the contribution of each feature in the output. So there are some assumptions about regression model. One of the restricting assumptions about regression model is assume that the output, which is a continuous value, is coming from a normal distribution. So the basic assumption is the y is sampled from a normal distribution with a mean and variance. So for many real examples, this is not true. So what we should do, there are some amendment to deal with this problem. For instance, if you have some exponential distribution data or some, you can use the log of the response, which looks like a Gaussian distribution. Another important point about the regression model, sometimes these coefficients, these features, there are some categorical data. The features could be categorical data. So there are some techniques we can convert them to some continuous value, or there a technique called one-hot encoding that we can deal with this sometimes binary or categorical data, which is our sample from a multinomial distribution, and then do the regression model. But what is important is to know what is the input, what is the output, what are the coefficients. So the training is, what are the task of trainings? You have a input, you have n sample pairs from the input features and the output, and then what you wanted to find the coefficient vectors. We wanted to find these A's. So, and then what will happen if you compute these coefficients, and if you have a new object, for this new object, you don't have the output, but you can do the measurement for input, then you can predict what is the output. So for example, for previous example, I gave you from the diabetes patients. So if you can fit a regression model by which you can, based on some measured value from that patient, you can predict the diabetes index, then you train your model, you obtain this coefficient, and then if you new patient come to the clinic, we don't need to, if you want to find the outputs, you already have the coefficient vector. So basically we multiply coefficient vector by the this feature samples from that patient, and then we can predict the diabetes index. So this is important to know what is the testing phase, what is the inference phase in a supervised learning problem. So when you compute the model parameters, when you know what is the function or estimation that function, then the task is to apply that one for the new data set. So also note that in terms of, I can write this one as in terms of a vector wise, this should be the yi, which is a scalar, is equal to the dot product between a, vector a, and vector x I. Okay, so this is, if you want to compute, basically we do a dot product, which is equal to multiplication of a transpose times x I. So that's, you may see in another context this compact form rather than this detailed form. As we show also, we solve the regression problem using this vectorized form, not using this detailed and scalar version. So that's the linear regression and the training, and also what is the testing. Testing is to having a new object with some measured features, and then we can predict the output. So let's take a look at okay, what we wanted to predict, how we can find the coefficients of a regression model having n samples, and then what the input and output relation looks like, and if you wanted to have a compact form in terms of some matrix multiplications, how this compact form looks like. So starting from here, so let's say we have collected n samples. For each samples now we have the pair of input and output. So the y1, assuming that we know the coefficient, is the coefficient is a0, a1 times x1, x2, and xp. Note that this super set, or the superset means the sample, and this subscript means the feature. So this is important. When we say x I j, you should know that this is the x, and this is the ith feature from the j sample. So this is the ith feature from the jth sample. So don't mix them up. So also for the last sample, we do the same. We have the first feature, second feature, and this is the value of the feature for n sample. And for all of them, the coefficients are the same because this coefficient is a function. So we wanted to have this function. You remember we have a y, let's say I, and then we have a function, and then we have an input I, which is a vector. So we wanted to find the output. So this function remains same for different input and output. What is difference is input and the output. So all these coefficients remain the same for different samples. So this is what I have. If I rewrite this one in terms of a vectorized format, then I'll get this one a vector, this is the vector y. So this is the vector of samples. So I have, let's say I have n patients. I have 500 patients, and this one is called the independent matrix, or the feature space matrix. And this vector is A is coefficient vector. This coefficient vector. So, and this is x is a vector. X is a matrix which contains the features collected for all samples. Each row or P contain P features for one sample, and each column, this is also important to know the difference between each column is contain all the first feature collected for all samples. First feature collected for all samples. So if I wanted to write in terms of compact matrix form, that would be y, which is a vector, equals to a, which is a matrix, and a is another vector. As you see, also the dimension in here matches. So a is n sample, and p plus 1 feature. You have the p plus 1 because one feature is the intercept, which contain all the columns are all 1. Because in here we just multiply x by 1, right? There is no feature. This is why we have 1 in here. And then the dimension of a feature vector is p plus 1 times 1. If you multiply these two matrices, note that we can also consider a vector as a matrix whose column or row is 1. If you do multiply, because the number of columns matches the number of rows, we can do the multiplication, and then multiplying these two would be vector of n plus 1. So always have in mind these dimensions, what are the features, number of features, and number of samples, because otherwise you may confuse and you cannot do the matrix multiplication. Okay, so this is a vectorized form of a linear regression, more compact, and also is easy to investigate. Now, okay, what is it? This is, we are still in the training phase. So the training phase was the phase that we wanted based on some training samples collected from the population, and each sample contained the feature vector and the output, which is a continuous value for regression. Now we wanted to estimate the function. The function in here is a regression, a linear function, which only boils down to some p plus 1 coefficient, and then we have a matrix, which for this matrix, what is known is Y is observed, matrix A, or in here X, in here A is also known, and the only unknown is vector coefficient. So can we solve this equation and compute the coefficient vector when we have these observed values for the n samples? So so how to compute a linear regression coefficient vector given sample? This is the training phase in a regression model. So given this equation, I just dropped the index for the sake of simplicity. Also note that what is Y and A are called, Y is usually called response or dependent variable, and A or column of A are called independent variable, regressor, or predictors, or covariates. In different contexts or books, they may use different terms, but usually the term of feature values is better. This is because these are some features which we collected from an object and we wanted to compute another feature or output from this feature vector. So then we wanted to estimate A. I won't go through the detail how we compute these coefficient, but I give you the final result. The final result for A hat, which is an estimate to the true coefficient, is simply a matrix multiplied by the dependent variable vector. So in here, A, we do, this is called a pseudo inverse of matrix A, where simply we transpose A multiplied by A and then inverse the result and then multiply it again by A transpose. This is the based on what is called the ordinary least square algorithm, or OLS. If you heard somewhere OLS algorithm, this is basically an acronym for ordinary least square estimation method. It's not that much complicated. Basically, if we wanted to see how we solve this one, we wanted to find A such that we minimize the difference between this vector and this vector. So if we wanted to minimize this one, we compute the norm of this vector. So if we want to compute the norm of this vector, we all know the way to do this. We can do an inner product. So if you multiply this one by the same vector, A times the vector, and then compute the root, and then find the value. So this is a cost function in our optimization. What you wanted to find, we wanted to find the value for A that minimized the norm of the error. So basically, we wanted to find the cost function or objective function is to find A such that the difference between A times A capital times lowercase capital minus A is minimized. And so then how to use it, we need to take the derivative, set the derivative to 0, and then from there we compute A. And then it can be easily shown that A is equal to this value. So this is also a matrix because it's a multiplication of a couple of matrices, and then couple of version of A, and that would be another matrix. Simply, if we call this one M, A is equal to M times Y, where M is the pseudo-inverse matrix. So for the most of the real applications, you never compute this one because the scientific libraries, they're all now compute the OLS and then give you the coefficients. But all you need to know about the process. What are you like trying to compute? What is the coefficient? What are the feature space? What is the output? These are the questions you need to answer. So let's consider a linear regression example, and then based on that, so I wanted to just now show through an example what we have discussed. So I wanted to here identify what is the dependent variable, what is the observed, what is the response, what is the independent variables, and what you want to predict. So this is a problem in which you wanted to predict the stock market price, which is a continuous value based on some features. So features we have collected are gold price, oil price, let's say Alibaba sale, and also Amazon sale. In other words, if you have these 4 features, can you tell me what is the stock market price today? So these are for 6 days. We have collected this data. We know that this is not enough samples, but let's say consider this one as an example. So what is Y in here? So if I ask you this question, what is the response value? What is the dependent value? So yes, so dependent value basically is in here Y. And then how many features we have? We have x1, x2, x3, x4. And then what I wanted to do is I wanted to just find that if y is linearly dependent or related to x1, x2, x3, x4, right? And if related, if I wanted to build y from these 4 features, what is the contribution of these features? So let's say if someone comes and say, oh, there is no relationship between Alibaba sale and a stock market value in the US, is okay. So I can set the coefficient of x3 to 0, right? But these coefficients are high for features if the value they contribute more. So let's say at the end of the day you found that only oil, sorry, in here I have this is oil, this is a typo in here. So only oil price is related to stock. So all other coefficients are 0. So what we wanted to do, we wanted to see if y can be computed as a linear relationship between a1x1 plus a2x2 plus a3x3 plus a4x4. So these are the coefficients we would like to compute. Okay, so if I have these coefficients, then let's say for 6 days, I solve the model and I find this coefficient. Then for next week, I can invest. I can collect the value of gold price, oil price, Alibaba, and Amazon, and then predict what is the stock price and invest if the model works, right? So in here, how many samples do you have? So we know that the number of samples is 6. So in our model, n equals to 6. How many features do you have? Number of features is 4, right? So now we know if you want to write down in terms of a matrix. So this is y, and this matrix is A, right? The A matrix which contains the features, and then we need to find the coefficients we need to find coefficients. So if someone asks you what is the equivalent for A3, so A3 in this table is, sorry, Y3. Y3, the stock at the third day is 200. And I wanted to see if I can relate this stock price based on some coefficients and A1, so times 50, so 200 in here is 90, plus A2 times 98 from the oil price, plus A3 times 3, which is Alibaba sale, plus A4 times 9, which is Amazon sale price. Note that these numbers, I just made up this number. There's no real value in here. These are very irrelevant to real values. So then I should be able, if I have the coefficients, I can see if the value is correct or not. So this is a regression problem. So all you need to do, just identify the input and output. So let's say we have a model. So in Python, so in model you pass the y vector, the input, which is a, and also you pass the output, which is y, and then that model will compute the coefficient a for you. And then you're going to test this model and then on unseen data. Note that we didn't see this. We use this training data to train our model, to do the optimization, to compute the coefficients. Now we wanted to use this model for some unseen data and check if the so if I wanted to really check this model, I trained this model, I found the coefficient, and then next week I will check the model to see if model can predict for new days. And if I check it for like 10 samples, 5 samples, and the results are promising, then I can say this is a very accurate model. Or I can say indeed there is a relationship between these 4 features and the stocks, and they are linearly they are dependent, right? So also we know that if some of these features they are not related at all, then we can ignore their contributions. We can ignore their contribution. Also, you can look at the regression model from another point of view in terms of vector-wise. We can say the vector y, so this is vector y, is equal to, so this is intercept, which is all A0, A0. So I can write in another way to make it simpler. Because, okay, I can write, let's use another color. I can say this is equal to A0 times a vector of all 1 plus A1, which is a scalar, times a vector of the first feature for different samples. So basically this is x11, x21, x31 to x61, and then continue these to get to the last feature, which is A4 times this vector, and this vector is x14, x24, and then x64. Okay, so this is another way of looking at the, and then I can call it one x1, x2, and so on and so forth. So this is another way we can look at the regression model. So basically the vector y is a linear combination of the other vectors. So a0 times vector 1 plus a1 feature 1 plus a2 feature vector 2 plus all the way to a4 feature vector 4. So a scalar times a vector. And then if each of these vectors is not related, or there is no correlation or no dependency between these independent variables and the response, the coefficient could be 0. So let's say if, as I said, if there's no relation between Amazon sale and the stock, so this coefficient is going to be 0. Or if there is a very high correlation between the oil price and also the stock, then this coefficient is high, right? So this coefficient determines the contribution of each feature in the output value. I re-emphasize these x1, x2, x3, x4 called the independent variables. They are also called sometimes regressors or predictors or covariate, and then y is called response or dependent variable in linear regression. So that's an example of regression models and how to compute the value and how to test it. Okay, so now let's say using some tools we managed to compute the coefficient vector. So we wanted to see how we can validate our model, how we can make sure that this model is a good model. In fact, this is one of the most important part of the in a data science pipeline when you wanted to do validation, or you wanted to also, it's called sometimes performance evaluation. So you wanted to see how your model works. And this is different techniques, different methods are used in order to evaluate the performance of a regression model. I have another full lecture how to evaluate the performance of a classifier, but here we focus on regression model validation. So usually we use 3 matrices in order to to see if the regression is a good fit or not. The first one is called R squared, also known as the goodness of fit. So if you consider a simple regression model when you have one input and one output, and if you have the scatter plot, and then when you're computing the linear regression coefficient, basically for this simple example is a straight line when you have only one independent variable and one dependent. We always have one independent variables. So that's a line. We wanted to see how this line will show the true relationship between input and output. So let's say consider the scatter plot on the left, so this one. So you manage for this data, basically each point in here, so this is x and this is y. So each point is basically represents, so this is, let's say, x. This is a sample. Each point is a sample. This is, let's say, this sample 100, and for this sample 100, we get the output 100, right? So, and then for other words. And then this line is how you find the best prediction. That means if you want to find a prediction for x1 based on this line, so what we do, we basically use this value, and this is the best estimation for y100. And this is a difference between the predicted and the true value, the predicted and true value, which is rather high. So one way to, if the variation of the samples in a scatter plot is rather high and far from the regression line. And note that this is a one-dimensional example. It's hard to visualize it when we have more features, but for two-dimensional, it's easily can be verified by a scatter plot. So if this line, the data are scattered around this line, so something like this, then the R squared value is close to 0. Whereas for the example on the right, this is a very good fit. As you see, the variance or variation of data are all within this bound. So they're so very close to the regression line. For this one, you will get a very good R squared. So R squared basically show if you get a small R squared, always visualize these two images to see, and then you can see, oh, this is a good fit or not. So if you, let's say for this example, probably you will get an R squared equal to 0.2. For this one, you get an R squared equal to 0.849. And also note that R squared is always greater or equal than 0 and smaller or equal to 1. 1 is the best you can get and 0 is the worst you can get. It's very hard in real problem to get an R squared. Sorry, this is R squared. I forgot to put this square in here. So it's very hard to get an R squared close to 0.9, but sometimes depending on application, an R squared close to 0.67 is also a good one. So don't be disappointed if you fit a model and R squared comes out to be like 0.7. Doesn't mean that's bad, or 0.5. Depending on your application, even a low value for R squared may make sense. But it's the first metric we use in order to see if our regression fit is a good fit or not. The second one is root mean square error. So root mean square error is basically if for each value of y, let's say for sample I, you get an estimation I hat, so this is the estimation. Ideally, we want this value be as close as possible to the actual response. So this is the estimated response, which comes from the regression model. It should be as close as possible to the actual value for training sample for which we have access. So ideally, I wanted to have yi minus yi hat small. So in order to make the error difference between the minus or plus, I take the absolute value and then also I square it. And then for all samples, I will add up this number. I will add up this number and try and then report the number. So if I wanted to, write down RMS in terms of the sum, so basically, usually we also divide it by n. This is the sum from I equal 1 to n of y1, this sample 1 minus y1 hat squared plus, this is the error from second sample, y2 minus y2 hat, estimated one, and then do is sum for all values yn minus yn hat squared, and then we take the square root of all of these values. This is called mean square error. I forgot here to put 1 over n. So this is how we compute the mean square error. And then we know that if you want to write it in terms of a vector, this is the inner product of y minus the vector y minus vector y hat. We do the subtract two vectors element wise. If you do the dot product, this is exactly as squared each difference and sum them up. So Mean square error is a very famous a cost function or objective function, which we also use that one in neural networks. We wanted so ideally we wanted to predicted value be as close as possible to the actual value. So then we find the difference for all samples, and then we take the mean to see how close is this value, and then we can compare it with different algorithms and results. The next one is called the analysis of residual, very close to the root mean square error. This is a visualization technique. So if you for each sample you compute the error, so the error from sample I and sample I estimated. So this is a value called, let's say, EI. EI is the error for ith sample. So if you have this value and then you have a scatter plot for the residuals, if you have a scatter plot for these residuals for different samples, what we expect to see, we wanted to have a symmetric plot around the zero. So some errors might be up, some of them, but overall they should be symmetric around the line 0. So if you visualize this residual, and this residual is symmetric and ideally not very scattered, that means this is a good estimation. However, if you found a case that this scatter plot is skewed towards somewhere, and then that's not a good sign of the regression. For instance, if you have an error scatter like this, so let's say they're good for here, and then suddenly you see errors go up here, they're not symmetric, that's scatter plot indicates that this regression model is not good. So for some data it works well, for some others it's not good. But for this one, it's basically the error follows a Gaussian distribution with 0 mean and unit variance, which is what we wanted to have. It is the first assumption we have on error. This one, however, is not a good fit. Okay, so these are 3 criteria we are usually used to determine if a regression model is a good one or a bad one. I recommend you calculate all 3 criteria, and the software we are using in scikit-learn automatically will calculate this one, their function easily. If you pass y and y hat vectors, they will calculate the all these 3 values. For residual, we need to do plots. There are also some software of Python. They do all calculations and they print out the results. And they are very popular in R because it was a very dominant language previously for statisticians, but now from data science point of view, because of the dealing with the big data, everything is migrated to Python. Okay, so another important issue we need to investigate when we are dealing with the regression model is to examine if our regression model suffers from what is called the multi-collinearity or not. This is a very severe issue, in particular when the dimension of feature space is high, and we need to make sure that our model doesn't suffer from multi-collinearity. So multi-collinearity is simple. If the features we have collected, they're correlated to each other, then the solution is not stable. And this come back to how we calculate, because in calculations of the coefficient, we need take the inverse of the matrix A, so we need to somehow compute A transpose A inverse. And if the columns of A are correlated, then the inverse of this matrix becomes 0. And then we have some numerical issues. So namely, we divide we have a division by 0, and this system is unstable. And in other words, intuitively, that means you have collected some features so that some of these features are redundant. We need to discard them because let's say if you have collected 3 features and you want to see the responses related to these features, if 2 of these features are correlated, that means they don't have, one of them is enough. We don't need to have 2, and then that's a redundancy. We can discard one of them. And also another issue is that when we are computing the coefficient based on the OLS, ordinary least square error, you are dividing by the inverse of the pseudo matrix doesn't exist, so that will be a huge problem. So you need to carefully consider this problem. Fortunately, there is an extension to linear regression model called ridge regression, which mitigate this effect significantly by introducing hyperparameters or a penalty term to the regression model. I don't want to talk about that in details in here because this will distract your mind from the linear regression models. But have in mind, multicollinearity is sometimes an issue in regression. You should first of all identify that, and also you should know how to take care of that using the ridge regression model. Okay, so now consider you have your data, you have given n samples, and then you wanted to train your model and do the test. So usually we have collected some data from a sample population. We don't upfront say, okay, oh, this data are for training, this data for test. For many problems, you are given the data and you are asked to feed a model and to test your model. So this is your responsibility, that split the data to some training and test, and then train your model on training data and test your model on test data. So then the question is, if I was given some pairs, so if I was given some pairs, let's say x1 and x1 hat, feature is vector, sorry, y2, x2, y3 and x3, and then it's continue going all the way to yn, last pair, xn, feature space. So how should I first of all train the model, compute the coefficients, and then validate our model and tell this is a good model based on test? As I said in the beginning of these lectures, that when I said we wanted to estimate the function f such that this function performs well on unseen data during the training phase. So one way is to randomly select a subset of samples from this sample population and train the model on the training set and then test the model on test set. Let's say what I do, I just randomly, let's say n is equal to thousands. I have 1,000 samples. Randomly, I will select a chunk from here which contain, let's say we call it m, 100 samples. 100 samples. So I have 1,000 samples in total. Randomly, I select a box, or randomly I select 100 samples for test. test. Okay, so I train my model on the training set, and then I test the model on test set. So this is a very simple approach, and also makes sense. All you need to do is just randomly select from your data a subpart and then do the test. Usually what we wanted to do, we wanted to have as much as data as we can for the training. So we usually use about 75 to 80% of our data for training, and then we use around 25% to 20% for test. If you wanted to do this, there is a function in Python from model selection. This is an auxiliary function called train test split. You are going to do this function a lot. This function, you basically pass a, it is in here, x and y. X is a feature space and y is the output vector. And then there is a initialization state that basically tells the machine start from a random clock. It doesn't matter what number you put in here. That makes it the data, if you're using data over and over, you're starting from different random clock, and data don't have any overlap. And then there is also another input argument in here. You can tell what percentage of data be for training, for test. So if you, let's say you put here 0.7, that means 70% of data go for training, 30% go for test. So this function has one more input argument. So then output of this function is two vectors and two matrices. So we have x train and x test. These are two input feature space, one matrix for the training, one matrix for test, and then we have y train and y test. Please spend some time to understand these outputs and these inputs. Otherwise, I've seen students when they wanted to test their model, they get confused. What is x train? What is x test? So x train is the input feature matrix as a subsample. X test is also the input feature for test phase. We also need to have the output labels. So y train is the outputs for the x train, and y test is the output for the x test. So if I want, this is a matrix of dimension, let's say for this example 900. Let's say we have 10 features. 10. X test is 100 samples, the dimension is 10. Y train is how many? Is 900 samples and dimension is 1. And Y test is 100 and dimension is 1 again, because the output is a vector. Okay, so this is a function we use to do the test and split. So this is a very standard way. However, there are some serious problems with this method. The first one is because data sometimes are scarce and we wanted to take advantage of the data, we basically lose 10% or 20% of the data for training. So we know that we have samples from a population. When we wanted to use these samples as much as we can to find the parameters or to find the function f as close as possible to our true function. But the problem in here is we are holding 10, 20, sometimes 30% of our valuable data for testing. That's one problem for splitting to test and training. Another problem, which is very serious, and in some particular data sets, has some very bad drawbacks, is when you are sampling your data, even though you do random sampling, your sampling might be biased toward one attributes or one way that the results are good. So you do the sampling, and then you get the results first time 90% accuracy. And then you do the second one, you get the result 10%. So that means the first time you sample the data from where these data are close to the training data, but the second time these data are not seen by classifier and the classifier has some problems. Let's say we have the data have this distribution. Okay, so that means these data are unlikely coming from this distribution. So we expect the model perform also well on these tails, right? If you randomly select samples from here, you may get good results. And then sometimes you may get samples from here, the results are not good. So what's the amendment in here? What can we do? The answer to this shortcoming of the train test split is called cross-validation. Cross-validation. So cross-validation is very simple. So in cross-validation, we first split our data to 10 folds or 10 segments, and then we test our model 10 times. So what does it mean? That means for the first iteration, so I split the data to 10 folds. I use the 9-fold for training and then the last one for the test. Okay, and then I compute the error coming from this part. And then for the next part, I will hold out this fold and then train the model on the gray parts. And then for the third fold or third iteration, I will hold out this chunk of data and then train it on the rest. And then I do all for 10-fold. Let's say I do the 10-fold cross-validation. So this is an example for 10-fold cross-validation. We call cross-validation by abbreviation of CV. CV stands for cross-validation. So this way, we take advantage of all data for training, and also the sampling is not biased because we use all data for training and all data for tests, right? So it is therefore recommended to use cross-validation when you wanted to validate your model. And then this computing error, this is the evaluation metric. It could be R squared, it could be the mean square error, it could be the residual, doesn't matter. This is a measure for performance evaluation. And at the end, what we do, we take an average of all these errors or the performance evaluation metrics. So in here we had 10-fold cross-validation. Therefore, we add up the 10 error and then take the average. So this way, we get a very good sense how our model is robust and do well for the during the test. So we use a cross-validation. Cross-validation has also another application for model validation and also for finding some hyperparameters in our models. Sometimes classifiers or regression models, they have some parameters, and then these parameters should be identified by using cross-validation. But for now, this is only one way to test your model based on cross-validation, to make sure that you have tested your model for all data, and then during the training phase you have seen all data. If these errors are not significantly different from each other, that means probably the model is robust and then it can do very well when you are presenting noisy samples. So we use the cross-validation. This is a very simple example. I copy and paste from the scikit-learn. So if you wanted to do cross-validation, I won't go through details, but so we wanted to, this is a diabetes example. I told you we wanted to predict a diabetes index for some features we have collected from from patients. So we have 150 patients in here. We get the input feature, we get the labels or output, and then we create an object for a type of a linear regression model is called lasso, but this is a extension of generalized linear regression, but it doesn't matter in here. What I wanted to show you, there is a function called cross-validation. So basically you pass your model. So this is the model you have created. It could be a linear regression model, or could be also a classifier or any supervised model you have created in scikit-learn. And then you pass the feature space, the entire X, and then output labels, and then ask for how many fold of cross-validation you wanted to do. In here, it's set to be 3-fold. And then the output is the error or error that from each of these folds. So you can also specify which metric you wanted to check. You want to an R squared, you wanted to do other metrics like F1 or anything else. So that will print out, and then you will take the average of this vector as overall performance of these classifiers. So the take-home message from this part is if you created an object which represents a classifier, if you present that class a classifier regression, you present that model to the function called cross-val score, and then present your data. This function automatically split the data to different folds and do the test and training, and then report to you the results. So for most of the application from now on, I would expect you to do the cross-validation. You can also do the split to train or test, but cross-validation gives you more robust results. So in order to wrap up what we discussed during this lecture, we introduced the topic of supervised learning, which is one of the most important topics in data science, and where supervised learning is used when you have label data, when you have an input and output. The goal is to find an estimation for a function which performs well for unseen data. And then supervised learning has two parts, classification and regression. In this video, we focus on regression models, and then we show that what is a regression model, what are the parameters, what is the input, what is the output, how we compute the coefficient vector, and how we evaluate our results, and how we do, what are the problems with the regression models, and how we do the cross-validation in order to have a robust performance evaluation of our model. In next video, I will talk about classification and also how we can evaluate performance of a classification. Then we will talk about two types of classifiers: logistic regression, which is related to the regression, linear regression, and neural networks. See you in next video. I wish you all a good day or night.